Hi class, welcome back for another lesson. Today's lesson is going to be about energy stored in an inductor. This is class by Raj teaching for Physics Form 6 Semester 2. The learning outcome for today's lesson is to use the formula for the energy stored in an inductor. Now what is an inductor? An inductor possesses inductance, L. An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this almost instantly. Being able to store and quickly release energy is a very important feature, and that's why we use them in all sorts of circuit. The magnetic field that surrounds an inductor stores energy as current flows through the field. 17.4 Energy stored in an inductor. Okay, so when they were talking about energy stored in an inductor, now what is an inductor class? An inductor is actually a component. Okay, inductor is actually what is a component in electrical circuit. Okay, is a component in an electrical circuit which possess inductance, inductance means L. Okay, so usually it consists of an insulated wire wound into a coil. So you look like as if like you have a conductor, a wire, you wound it into a coil. So if this is an inductor, that means it is a component in the electrical circuit where the function of an inductor is to store energy in a magnetic field. Okay, in a magnetic field, it stores energy in the form of magnetic field. Okay, that means when it stores energy in magnetic field means if the energy increases in the inductor, then the strength of the magnetic field increases. So that's how it stores energy. Now the concept here is when a voltage is applied across an inductor or self-inductance L to drive a current through the inductor, the most important thing we're going to look at is this sentence. The potential difference across the inductor must be equal to or greater than the back EMF. Okay, now I have a diagram here which I'm going to draw. Okay, so this is a diagram. This is a coil, okay, which is connected to a power supply. Okay, so here this figure we have a solenoid here, okay, with the inductance which is L, all right, and then we have current that flows from this applied voltage. This is applied voltage. Okay, and then we have current flow into the inductor. Okay, into the inductor, all right, which is self-inductance is L. Now in order for the current to flow, to drive through, okay, to drive through the inductor, the voltage applied must be equal or greater, but I'm going to take equal, yeah, equal or greater to the back EMF but in the opposite direction. To the back EMF but opposite direction. Okay, so if this is the direction, this is applied voltage, back EMF is in this direction as we have learned in our previous lesson. And if you look at the sentence is in page 213, our Oxford FAJAR book. It says what? The potential difference across the inductor must be equal to or greater than the back EMF. Potential difference across the inductor means applied voltage. Okay, across the inductor means is the applied voltage. So this voltage Okay, must be equal or greater than the back EMF in order for the current to drive through the circuit or to drive through the inductor. Okay, alright. So applied voltage is equals to negative E back. Okay, back EMF, where we know back EMF from our previous lesson. Okay, E is equals to negative L di over dt. Okay, and then we substitute inside here, we get what? We get V applied, which I'm going to put just app. V app is equals to L di over dt. We just substitute inside here. Okay, now we want to calculate now power. Power in the inductor. Power inside the inductor. For power in the inductor, okay, power in the inductor is equals to IV. Okay, current times voltage. Alright, so applied voltage, I, what is V? V is this, IL di over dt. Okay, alright, so what do? We know power. We know power is energy over time, so this one becomes du over dt. Okay, then du is equals to IL di. Okay, then what we do is we integrate. Okay, we integrate. Okay, then what do we get? We get the formula U is equals to half Li square. Okay, because L is a constant, you see. So when L is constant, we can bring L out. So I di. So once we integrate, then we get the formula U equals to half Li square. So this is the formula. So our learning outcome wants us to know how to use the formula. Okay, so use the formula. So we have to learn how to use the formula. Okay, so if you look at your textbook, you will see the same thing. V equals to negative E back. Okay, which comes from this sentence here, which is the concept is the potential difference across the inductor must be equal to or greater than the back EMF, but in the opposite direction. That's why you have the negative. Okay, for the current to drive through the inductor, Okay, then we find the power in the inductor, and then we will get the answer for the energy stored in the inductor. So this is the formula, the energy that is stored in the inductor. Now in the inductor, you must understand the energy is stored in the magnetic field. Okay, energy is stored in the magnetic field because in the inductor, because solenoid, alright, we have a magnetic field due to the electromagnetic induction. So due to that, energy is stored in the magnetic field. Okay, now when the current in the inductor is not constant, okay, if the current in the inductor is not constant, that means this current is not constant, then if the current is increasing, okay, if current is increasing, usually current in the inductor is not constant, it might be that it is a AC circuit. Okay, it might be it's a AC circuit. For DC, it only happens when switch on and switch off. Okay, so this one is telling us for an AC circuit. Okay, so dL over dt is positive. Okay, how do we do this? But we will be learning this in the next chapter. Okay, but just explain of what is this about. Okay, when the current I is increasing, di over dt is positive. Okay, di over dt is positive. Okay, keyword number 1. Now what does it mean? When current is increasing, that means your final current is bigger than your initial current. So I put example, final current is 5, initial is 0. Okay, so this will be a positive value. This will be a positive value. So positive here, positive will give you power positive. So that's why it says power positive. Okay, alright, positive power indicates that the inductor is receiving power from the voltage supply. Okay, this one we'll be learning in the next chapter, more detail in the next chapter. Okay, Now, when the current is decreasing, that means decrease. So your final is lesser than your initial. So if I have a maximum is 5, so it will be 0 minus 5, correct? Your final is 0, your initial is 5, because decreasing ma. So 5 decrease to 0, correct or not? I give example only. So this value will be a negative. So your di over dt will be a negative value. So negative value means this is a negative value, power is a negative value. So it gives you power is negative, number 2. So negative power indicates that the inductor is returning power to the voltage supply. I'll be teaching this in the next chapter. Okay, this is just a knowledge of how the energy is stored in the inductor. Why is positive, why is negative. Okay, then so the lesson for today is we just need to use the formula, and how we got the formula is from the concept of electromagnetic induction. Alright, okay, that's all class.
The difference between an inductor and capacitor. Capacitor, it opposes a change in voltage, but inductor, it opposes a change in the current. Capacitor stores energy in the electric field, inductor stores energy in the magnetic field. The unit of capacitance is farad and the unit of inductance is Henry. It resists changes in voltage. That's what a capacitor do. Inductor, it resists its changes in current.